All right, let's do kind of a hodgepodge today. And we're going to do some derivatives of trig, which you've done before. So hopefully you can remember all these 6 derivatives. So practice and see if you get those correct. And remember sine, derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. Squared, ugly chew. And the derivative of secant is secant tangent. And this is negative cosecant cotangent. So all the C's are the negative ones. Now I want to talk about one more because I don't want you to make your life harder than it needs to be. We did questions like this earlier. If I have the derivative of 5 sine of x, you just said, well, I've got that constant, and he kind of comes along. I want to be very clear that you go, but wait a minute. Isn't this a product? Isn't it 5 times sine of x? But we did these problems last unit, and I hadn't mentioned the product rule. So I'm not saying the product rule doesn't work for something like that. I'm saying you don't need to make your life as hard. When you have to do the product rule is when you see 2 variables of x. If that said 5x times sine of x, then you must do the product rule. What I want to get you to see is if I just have a constant, I bring the constant along. But notice, friends, it's not that the product rule doesn't work. It's just that I'm making it too hard. Because look, if I considered 5 to be my first and sine to be my second, and I did the product rule, I would do 5 times the first times the derivative of the second would be cosine, plus the second would be sine, but look at this part, times the derivative of the first. If the first is a constant, this would be 0, and it goes away, so I just get this. That's why I don't bother to do the product rule when I just have a constant times something. I just bring the constant down. It's not that the product rule doesn't work. But when I get to this example, example 1, oh, I better be doing the product rule, actually twice, because I've got 2 different products that I have here. So I have to look at this 4x and this sine of x, and then I have to do the product rule on this term to the right. I will tell you, I tend to put that minus, I change this to a plus and put the negative with the negative 2x squared. That's the way I like to do it. So try to do the product rule twice on these. So stop the video, try the product rule, and then come back and see if you get it. So what do I have here? I have f prime of x. Okay, product rule twice. So I'm looking at 4x being my first and sine of x being my second. So I'm going to go first times the derivative of the second, which is cosine of x, plus the second, which is sine of x, times the derivative of the first. So I'm just going to slap a 4 in the front. So that's that one. Now do the next one. Okay, I'm going to put a plus. Now I'm going to consider my first to be negative 2x squared and my second to be cosine. So first, negative 2x squared, times the derivative of the second, that's negative sine x, plus the second, which is cosine of x, times the derivative of the first, and that would be negative 4x. Now what do I really have? If I need to clean that up, I could have 4x cosine of x plus 4 sine of x. That one would change to be positive 2x squared sine of x, and then minus 4x cosine of x. And then what happens? Well, gosh, this term and that term go away, And how I write my final answer is, of course, up to multiple choice. I could certainly leave it like that, which is a perfectly wonderful answer. Sometimes in multiple choice they say, oh, let's make them do a little bit more math. So what math could I do there? Well, I could factor. So if the multiple choice answer factored out a common term and left the answer like this, well, you of course would have to then do that math to get that. So again, both of those answers are correct. It just depends how the multiple choice is. If it's free response, I'd of course accept both. So we're moving beyond the simple trig now. We're just, excuse me, we are putting the trig in with product rule, quotient rule, and that sort of thing. So you've got to know the basics, but we're being a little more, doing a little more difficult ones than we did last unit. So again, you try example 2. I see a quotient, so I'm going to think quotient rule. So I have my HO, D high, derivative of secant, is secant tangent. HO D high minus high times the derivative of the bottom. The derivative of the bottom, derivative of 1 is 0, derivative of tangent is secant squared. All over, ho, ho. And obviously, again, I could kind of, depending on the answer choices, but I'm just going to distribute that stuff out, and that's really as good as I can get it, I suppose. So I'd have secant of x, tangent of x. So I'm just distributing there and now here, plus secant of x tangent squared minus secant cubed all over, and I'm just going to leave this. Again, they could trig identity that possibly, but with trig, you certainly know in multiple choice that I could trig identity things to death. So it just depends what that multiple choice is. So you'll be doing more trig stuff, more difficult trig stuff on tonight's homework. Now let's look at some other things. What just happened? Let's look at a piecewise function. A piecewise function, you just have to find the derivative of the individual pieces, but then you've got to be careful, and I'll show you what I mean about the break. So if I have a piecewise function, I can say, well, all right, I'm just going to do f prime, and it's going to be in pieces as well. I can do the pieces very easily. The derivative of that top function is -2, and the derivative of the bottom function is 2x, so that doesn't seem too hard. Here's where the issue, or where you have to be careful, comes into play. I have to see if it's differentiable at this breakpoint. Now remember, I'm going to do that in the fastest possible way I can. First of all, I'm going to see if the function is continuous there. Because if it's not continuous, then it's not going to be differentiable. So I won't put an equal to. In other words, I'm trying to determine if I need to put an equal to on one of those inequalities. So is it differentiable at 1? So I certainly am going to see if it's continuous. In my head, I'm going to plug in 1 here and go, the y value would be 1, and I plug it in the bottom. It is 1, so it is continuous. So can I automatically now go, oh, sweet. So since it's continuous, I'm going to put an equal to on one of those ones. No, because remember, continuity does not imply differentiability. Just because it's continuous doesn't mean it's differentiable. What I now have to see is I have to do the same kind of thought like I did here with the derivative, because I don't have to do the limit statement, thank goodness. I could, but let's do it faster. I could look and say, if I find the derivative to the left, do you see that my derivative from the left is going to be negative 2? Because there's nothing to plug into, so my derivative is negative 2. My derivative from the right, if I plug in 1 into here, I would get 2. Is the derivative from the left and the derivative from the right the same thing? No. So what does that mean? That means it is not differentiable at x equals 1. Therefore, I cannot put an equal to on 1. I can't just copy those inequalities. So my final answer is that which is in red. Notice I just have the less than and greater than, and that would be my derivative. Now, if I get the derivatives to be the same here, then I will need to put an equal to. And it really doesn't matter which one you put it on because they're the same. So you try example 4. All right, in example 4, I do the same thing. I usually end up writing my derivative first, and then I worry about the break point. So the derivative of the top, that's just 8. Derivative of bottom is 3x squared minus 4. Now, I know this is going to be x is less than 2, x is greater than 2, but I need to check at 2. I need to see if it's differentiable at 2. Well, is it continuous? If I plug in 2 there, that's 16 minus 16, so that would be 0. If I plug in 2 here, 2 cubed is 8 minus 8. I also get 0, so, and there is an equal sign, so there is continuous, so I unfortunately have to do a little more work. Because remember, if it's not continuous, I stop. I don't put the equal to because it wouldn't be differentiable. Now I do the same thing in this line. If I plug in 2, the derivative from the left, so here's the derivative. So the derivative from the left is going to be 8. The derivative from the right, what is that? 2 squared 4, 4 times 3 is 12. 12 minus 4 is 8. So this function is differentiable everywhere. So I would put an equal to, it doesn't matter. Generally speaking, they tend to put it on the same one it was in the original. So I'm going to put it on that bottom one, but technically it does not matter. So I just want to point out, not that you have to write this. Again, my answer is that in red, but I want you to be clear that the derivative at 2 is equal to 8. The left and right derivatives are the same, and so that function is differentiable at all places. Okay, so we've done trig, we've done piecewise, and now we have to do absolute values. Now I'm going to be honest. You could do absolute values 2 different ways. One way is to write the absolute value as a piecewise function and then do what I did up top. And that's fine, and that's wonderful. But I do think you're able to do it a little bit faster. And here's why I say this. Let's just look at this graph real quickly. Could you graph for me 2x minus 9 pretty quickly? I mean, hopefully you would say, yeah, it's that v, and it's just kind of shifted and stretched a little bit, but the general shape of it is going to be that v and it's moved over. Well, remember how you find that sharp turn point is when you set what's inside the absolute value equal to 0. So I would get x equals 9/2. So knowing that, I'm not going to draw an accurate 2-scale drawing of this graph, but I'd certainly know that this sharp turn is at 9/2. So I know my graph, and it's a positive absolute value, so I know it's going to be facing up, so the v is going to be facing up. Now remember in pre-cal as well, if I ask you the slope of this line, what would you say? Well, you go, well, gosh, I'd be graphing this line, so it's 2. Well, isn't the slope of that line the derivative at that point? So don't I know that f prime, when I look at that graph, I know when x is greater than 9/2, the slope of that line is going to be 2. When x is less than 9, don't know why I put a negative, when the slope is less, when the x is less than 9/2, what is the slope of this line? Well, it's 2, but it's -2. It has the same slope, but it's slanted negatively, so I already know that. So aren't I done? I don't have to rewrite the whole equation. I just I know one's going to have a slope of 2 and one's going to have a slope of -2. I just have to figure where. Do I have to worry about putting an equal? I hope that you know that, of course, you're not going to put that equal because the derivatives from the left and right are not the same, and I'm done. So you have to realize this number in front of the x, that is going to be the slope of the lines. Now, obviously, again, this way works if what's inside the absolute value is linear. If I had a question where what's inside the absolute value is like an x squared, then I would be forced to rewrite it and do it that way. So I want to be very clear, and I'll just do this one both ways, and then you can pick the way you like best. But what I'm saying about rewriting, remember we did that before. You did it in pre-cal where you rewrote f of x and said f of x would be 2x minus 9 if x is greater than or equal to 9/2. So I'm thinking of this graph and just rewriting the function. And then x, what is the equation of that line? Well, it changes the slope, changes of what's inside the absolute value. So this line would have an equation of -2x plus 9, and that's when x is less than 9/2. So that's rewriting the function, and then if I wanted to take the derivative of that function, well, those are very easy. So again, if what's inside the absolute value is linear, I choose to do it graphically. It's faster to me. But all I'm saying is, again, if you had something like an x squared in there, you'd be forced to do this step and then take the derivatives of each. Let's look at, you try to do example 6 however you like. So I'll give you a second, I'll erase here, and then you can see what you get for example 6. All right. I do see a linear inside that absolute value. So personally, again, I would do it graphically. And when I say graphically, I don't mean that you have to draw an accurate to scale drawing of that. Here's my thought process. I go, okay, where's my break point? You probably can tell from looking, but your break point is you set what's inside the absolute value to 0 and you get your break. So x is going to be 3. Now, as far as the graph, you have to think of transformations, and really, you're moving to the right 3 and up 1. But then this thing is important. What is that going to do? It's going to flip the graph from being a V that's facing up. It's going to be a graph of a V that's doing this. What are the slope of those lines? Well, what number is in front of this x? 1. So I can write my derivative. F prime of x. When x is greater than 3, that means to the right of 3, what is the slope of this line? Is that slanted positively or negatively? You're like, negative. So that one's going to be the -1. When x is less than 3, this line is the positive, and that's 1, and I'm done. So I like that way. So you're doing some different things today. Practice the product, quotient, rule, absolute value, piecewise, all that fun stuff. All right, cool deal.